mentioned binomial theorem. Does that mean anything to anyone in here? Like you remember what you were doing or how you did it?
Isn't it right where you have the Pascal's triangle?
Yes, Abby's going to trail off now. Okay. Yes, it has something to do with Pascal's triangle, which is one of my favorite things to learn about in math. So it does a lot of cool stuff. So Pascal's triangle is involved. And then there is some other stuff there as well that Abby is talking about. Anybody else have anything they want to add about what binomial theorem is or what it does? What is it? Yeah, I think so. So like what is binomial theorem doing? It is expanding binomials that are being raised to different powers. So like the x plus 5 to the 10th power, so maybe that's what you're thinking, like really big powers. And instead of having to do x plus 5 times x plus 5 times x plus 5 10 times, we can use some patterns from Pascal's and binomial theorem to help us out. So before we actually get started on binomial theorem and the problems, which should be mainly reviewed from last year, I do want you just to take a little bit of time because it's kind of nice to remind ourselves of some patterns. So I have on this screen a binomial x plus y, so I have a first term plus a second term, and it's being raised to a power, so I have a power of a binomial, and that's what the binomial theorem is addressing. How do I expand x plus y to the n? Okay. And then down here I have several values of n. So notice I'm going x plus y to the 0, x plus y to the first, x plus y squared, x plus y cubed, fourth and fifth I have. Okay, and I could keep going. But what I want you to discuss with your table groups for a couple of minutes is what are all of the patterns that you see? Because the patterns that we see from line to line are going to be kind of like how I use binomial theorem so that it's easiest for me. So like we've already discussed Pascal's triangle a little bit. You can address that with your small group, but remind your small group like there's more than just Pascal's triangle at play here in terms of pattern. So what are some of the other patterns that you're seeing? And after a couple minutes, we'll just kind of share out what are some of those patterns that we're seeing from one line to the next as we increase the power to which we raise the binomial. Does that kind of make sense? Okay, so go ahead, take a little bit of time, chat it up with the people around you. What are some patterns that you're seeing? And then I'll ask you to share them. I'm going to move it real quick so it's a little bit higher. Okay, as I'm walking around and eavesdropping on your conversations, there's some really good patterns that we're discussing. So can you share out some patterns that you see as we expand the binomial? Q.
So, whatever exponent is 2, so like, it would be x to the 5th, and then as you move to the right, it would be x to the 4th, to the 3rd, to the 2nd, and then y would be to the 5th, and then move to the left.
Okay, yeah, so when you start with something raised to the 5th, here we're going to say x, it's whatever the first term is, right? So I could do y plus x and then they'd be switched around. But whatever the first term is, it's going to be raised to the highest exponent to start, so you give it the whole power. And then as it goes to the right, it goes down by 1 each time. Excellent, so that's a 1. And then what's the power of x right here on y to the 5th? 0, right? So x is 0, it's 1, you don't even see it. And then the y's, or the second term in the binomial, does reverse, right? So it actually starts at 0, so this is really y to the 0, and then it goes up as you go to the right, or like he was describing it, if you go from the right to the left, it should be going down. Okay, so good. I think that's a great pattern, and that's going to be really helpful to us as we expand binomials. I use that pattern in binomial theorem all the time. Are there any other patterns that you saw? Maggie.
The triangle.
The Pascal's triangle, right? And where do you see Pascal's triangle?
Like, what's the coefficient?
The coefficients to each term is the numbers from Pascal's triangle. So remember, to produce Pascal's triangle, you start with a triangle of 1. Okay? And then to get the next row, it'll start with a 1 and end with a 1, and then you add the 2 closest to get your other term. So 1, 2, 1. Next row will be 1, 3, 3, 1, 1, 4, 6, 4, 1. And usually we go up to about the 5th value, which is really like the 6th row of Pascal's triangle. Okay, but we could keep going, couldn't we? Okay, excellent. And Maggie is saying those are represented in these coefficients. So we have 1, and we have 1 and 1, 1, 2, 1, 1, 3, 3, 1. Now, we'll always see those in the beginning. Be aware that if there are other numbers in the binomial where we have x plus y in the binomial, if there's like a 2x plus 3y, those things are going to get raised to exponents, and then in our final answer, we'll no longer see Pascal's triangle. But Pascal's triangle will be there in our work. Okay, so excellent. I use Pascal's triangle, great. And the other thing I'll note about Pascal's triangle is, like, I label the rows of Pascal's triangle for myself starting at 0. So I call that very first one row 0 because that corresponds with the power of 0. And then this would be row 1, row 2, and row 3. So if I am raising a binomial to the 3rd power, I know to go to row 3 of Pascal's triangle, which is actually the 4th row of the triangle, 1, 3, 3, 1. Okay, so if you label them 1, 2, 3, 4, and you just know it's one more, that's also okay. Good. So Pascal's triangle, we got the exponent thing. Any other patterns that you noticed that you could share out? Something that I use, like a quick check for myself, it has to do with what you described, like where one is going down and the other is going up. But I can make sure I always have the correct exponents because the 2 exponents in each term should always add up to the power. So like in the first term, 5 plus 0 is 5. In the second term, 4 and 1 is 5. 3 and 2, 5. 2 and 3, 5. 1 and 4, 5. 0 and 5, 5, right? They always add up to 5. So that's another way for me to just make sure I'm doing the right thing with my exponents. Good. Okay, so on the next slide is the actual binomial theorem, which you should write down. Okay. I don't necessarily memorize the binomial theorem, though at this point I do know the binomial theorem. Been teaching it for a while. But I really put my focus when I'm trying to expand with binomial theorem on patterns. So I really build off of Pascal's triangle and then the patterns that both Hugh and Maggie described for us. the number of these terms that you're going to have to add together will depend on whatever the power of the binomial is. So, you know, if we look back at that previous slide, that very first one was raised to the 0 and there was one term. When it was raised to the first, there were 2 terms. When it was raised to the third, there were 4 terms. So there's always one more term. And that's because the first term is going to start out with a combination of n, which is whatever power you're raising to, choose 0. And then you start to go up and choose 1, and choose 2, and choose 3, all the way to n choose n. Okay, so there's always one more term than the power. And the other piece, so you've got a combination there, and I don't actually, I'm going to talk about these combinations here in a minute, but I don't actually calculate combinations when I do binomial theorem. I use Pascal's triangle, because they are combinations. The other pieces are, you got to take the first term in the binomial and raise it, like give it all the power, so raise it to the n. And then as you go, it's going to be 1 less, 2 less, 3 less, 4 less, until at the very end, that first term is being raised to 0. And finally, you'll have also the second term in the binomial. Remember, start it with the least possible exponent, which would be 0, and then work yourself up so that in the last term it's raised to the full power. So I'm just going to flip back really quickly to that slide before. So one of the reasons why I love Pascal's triangle so much is that it does so many things. And so Pascal's triangle, all of these numbers in Pascal's triangle are the combinations that you calculate in your calculator. So in this first row, row 0, this is a combination of 0 items chosen 0 at a time. In row 1, the first one is a combination of 1 item chosen 0 at a time. The second number is a combination of 1 item chosen 1 at a time. Then we do combination of 2 choose 0, combination 2 choose 1, combination 2 choose 2. Combination 3 choose 0, combination 3 choose 1, combination 3 choose 2, combination 3 choose 3. So that's why we use Pascal's triangle with binomial theorem, is we don't actually then have to do that calculation in our calculator. As we progress up on a combination, we're going to get those numbers in Pascal's triangle. So really cool. Let's do an example. On this particular example, because this is my first example in the notes, I'm going to do more work than I normally do. So I'm going to build off of that combination that, or the binomial theorem that I saw on the previous slide, which starts with a combination. So if I were trying to expand x minus 3 to the 4th, I would start with a combination of 4 choose 0. Always start with the least amount. Then I'm going to take the first term, which is x, and I'm going to give it the full power, which would be 4. And then I'm going to take the second term, which in this case is really a negative 3, so watch out for those negatives. And that would be raised to the 0. Notice the number that you choose always matches the exponent on the second term, 0, 0. Okay, that's another pattern. And then I'm going to add to that a combination 4 choose 1. Now my first term exponent is dropping by 1. My second term exponent is increasing by 1. We okay with what I'm doing? If you have a question, pop in, ask that question. Someone else may have the same question. And I'm going to try to squeeze all mine in here. All I'm going to do. So I've written out all my work. I have it like it's represented in the binomial theorem, where it's a combination times the first term raised to a power times the second term raised to a power for each term. And I can see my combinations are increasing. Choose 1, 2, 3, 4. My first term exponent 4, 3, 2, 1, 0 is going down, and my second term's exponent 0, 1, 2, 3, 4 is going up. Now, on the next line, I've seen a lot of people in past years have success if they're doing their work. Like, there's always a combination of first term and a second term, and those things get multiplied together. So when you're showing your work, people have done really well if they have like some kind of grouping system, whether you use parentheses or you use brackets. So that's going to be like the first term, the product of all those things. This combination 4, choose 0, I'm going to pull from Pascal's triangle, which I would call row 4. Some of you might call it row 5, and that would be 1, 4, 6, 4, 1 page. Correct. Remember, this is my first example in the notes, so I'm doing more work than I would normally do. I'm going to model it after binomial theorem. So this is going to be 1 times x to the 4th times 1. Then I'm going to add, and I have a new set of 3 things that need to be multiplied, so I'm going to group them together in the brackets, or you could use parentheses. If you don't need them, you don't have to use them. They're just helpful for some students. Second term, combination 4, choose 1 is 4, times x cubed times negative 3, plus 6 times x squared times 9, plus 4 times x times negative 27, plus 1 times 81. And then to get my final answer for the expansion, it should look like a polynomial. If I were to do x minus 3 times x minus 3 times x minus 3 times x minus 3, I'm going to get something quartic, degree 4. So multiply the things inside those groups. I should have x to the 4th minus 12x cubed plus 54x squared minus 108x plus 81. And I've expanded with a lot less work than doing that what I would consider like manually. X minus 4 times x minus 4. And then multiply by another x minus 4. But yeah, addressing Pedro's question again, you have to show the combinations, not if you pull directly from Pascal's triangle. So my next example, I'm not going to show my combinations. But they really are coming from that binomial theorem. So that's what the combinations are. Anybody got any questions? Where did I get a number? How do I do that thing? Okay, now I have one more example that I want to show. And I would suggest maybe jotting some part of this down in your notes. Because this is the one that I kind of like worry about the most, people missing a small detail here. So I have quantity 2x plus 5 raised to the 5th. Now on this one I'm going to do less work than I did on the last one. So because I'm raising it to the 5th, I'm going to go to row 5 of Pascal's triangle, but I start at 0, so some of you might call that row 6. But that row is 1, 5, 10, 10, 5, 1. And instead of writing out my combinations, because that's kind of tedious, I'm just going to go ahead and immediately replace the combinations with those coefficients. So I'm going to do my first term, would be 1 times, the first term is 2x, give it the full power, times y to the 0. Notice that I'm putting the first term 2x in parentheses. That's the small detail that I'm worried about. And then continue. 5 times 2x to the 4th times y to the 1st plus 10 times 2x to the 3rd y to the 2nd and 10 times 2x squared times y to the 3rd 5 times 2x to the 1st y to the 4th and 1 times 2x to the 0 times y to the 5th. what am I worried about people calculating, Maggie? I don't? Oh, yeah. Okay, that's the problem. I was like, wait. Okay, now, I agree. So I'm worried that people are going to, when they're simplifying, they're going to say 1 times 2x to the 5th. This is really 2 to the 5th, x to the 5th, so it's 1 times 32x to the 5th. Okay, so this is 1 times 32x to the 5th times 1. This is 5 times 16x to the 4th times y. This is 10 times 8x cubed times y squared. Ten times 4x squared times y cubed. 5 times 2x times y to the 5th, 4th. And 1 times 1 times y to the 5th. So that would be my concern, is that if there's a coefficient in the binomial, that you don't raise that to the power as necessary, but it should change. Okay, it shouldn't be 2x to the 5th, 2x to the 4th, 2x cubed, etc. So my final answer would be 32x to the 5th plus 80x to the 4th y plus 80x cubed y squared plus 40x squared y to the 3rd plus 10x y to the 4th plus y to the 5th. Questions, concerns? For the second term? No idea. It's supposed to be 80. Thank you. Should be 80. Any other questions? Yes.
Wouldn't like to the y
Nope. I mean, it's not a real polynomial because it has x and y in each term. But I would leave it to, like, think about that very first slide I showed. What are, like, you could see real patterns here. X is starting at 5 and going down by 1. Y is starting at 0 and going up by 1. So I would leave it alone. Any other questions? Okay, now there are just a couple of other types of questions that I can ask using the binomial theorem, so you got to do a little bit of thinking here. So if I asked you to just tell me the 5th term of a plus 2b to the 8th, how would you go about doing that? I'll let you guys talk with your groups real quick, and then we'll share out ideas. How could you find the 5th term of a plus 2b to the 8th? Then expanding the whole thing? Yes. Okay, let's regroup and share out some ideas. So there's a shortcut finding the 5th term as opposed to expanding the whole thing, right? I don't need the first second, third, fourth. They just really want the fifth term. So what I would do is sort of think about each term in a binomial expansion. I like to write mine like this. There are some holes there, right? I don't know how many I'm choosing. I don't know what to raise my first term to, and I don't know what to raise my second term. That's what I have to think about. So you have to think carefully here. If you wanted the fifth term, what number in the combination are you choosing as the fifth one in? And you have three answers, 4, 5, or 6, right? What do you start with? Combination, 8, choose 0. So the first term is 0, the second term is 1, the third term is 2, so the fifth term is 4. Okay. It's always one less. Choose one less. Because you start at 0. The first term is 0. So everything is one less than you think it will be. So this will actually be 8, choose 4. And then remember, the number that you choose always matches the exponent on the second term in the binomial. So it would be 2b to the 4th. And this one is not a huge deal because the other one is 4. Now, you should actually get the term, right? So expand as necessary. I'm not going to do that. Could you find the seventh term then of 3x minus 2y to the 10th? Page?
It's not always going to work out where they're both going to be.
No. Right.
So is there a way to like, figure out what you can count down from?
I choose one less. It's always one less.
So look for the exponent of a.
Well, this is always going to match this, and then they have to add up to 8.
Oh.
That was my pattern that I had. How many are we going to choose here? Choose 6. That matches the exponent for 3x or negative 2y. Negative 2y. So then the exponent for 3x is 4, because these two exponents have to add up to the power 10. So that'll make it nice. It's tricky because you have to remember it's one less. Think about what the very first term in the binomial theorem is. Okay. And then my final question, phrased a little bit differently but sort of the same idea, is find the coefficient of the a x to the 8, y to the 6th term in the expansion of x squared plus y raised to the 10th. I sort of do the same thing with my setup. Like, there's a combination, there's the first term to a power and the second term to a power. And then I use whatever term they're telling me, like, what are the exponents in that term? What do you know has to be true about these exponents in order to get x to the 8th and y to the 6th? Why does it have to be 10 combination 6? It matches the second term, and in order to get y to be y to the 6th, you have to raise it to the 6th. And then the exponents have to add up to 10, so this has to be 4. That also gives me a power of x to the 8th, because they get multiplied. And then I will get 6 right there. So on this one, it asks about a coefficient. You really only need the number, not necessarily the x to the 8th and the y to the 6th. Tatum, did you have a question?
Is A like the coefficient?
Yes. Your answer is the number A.
So that's Yeah.
Now, on this last slide, I'm not doing any actual calculations, but you should do that on your homework, right? You should actually plug it into the calculator and see what it is. Any questions? Be thoughtful on those. That's the best I could say. Okay, your homework assignment here. You have all the information for semester 1. Yay. We're going to do a review on Monday, quiz on Tuesday, review on Wednesday, test on Thursday, review on Friday, review on Monday, final exam Thursday.